derivatives on volatility. Here we will first talk about volatility futures and options, then we will move on to variance swaps. When talking about volatility futures and options, step 1 is to understand the CBOE volatility index or VIX. This is also called the FAIR index, and it is a measure of expectations of volatility in the S&P 500 over the next 30 days. This is called the FAIR index because when there is concern about the stock market or there is fear that the stock market might go down, the volatility increases. This is the implied volatility which increases, which means that the VIX index goes up. Now, this implied volatility is calculated based on options on the S&P 500 index. So if we look at options that expire over the next 30 days, the implied volatility of those options is used to come up with the VIX index. The greater the uncertainty in the market, the greater the implied volatility and the higher the VIX index. The next point is that direct investment in the VIX index is not possible. Therefore, investors must use VIX index futures to take a position on volatility. VIX futures allow an investor to implement a view depending on expectations about the timing and magnitude of a change in implied volatility. Now let's take a simple example to understand this. Over the next 3 months, the consensus view is that the market will be generally flat, and based on this view, the implied volatility is at an average level. But your view is different. Your view is that the market is going to crash and the implied volatility will increase substantially. If this is your view, then you can take a long position in VIX futures, because if you end up being correct, then the VIX futures will go up and you will make money. The next point has to do with the shape of the VIX futures curve. This shape is always changing and it reflects the current volatility environment, investors' expectations regarding the future level of volatility, and the buying and selling activity in VIX futures contracts by market participants. When we talk about these VIX futures curves, they are like any other futures curves that we've discussed in other parts of the curriculum. So here we will have futures prices, or specifically VIX futures prices on the y-axis and different maturities on the x-axis. So we might have contracts that end in April, then contracts that end in May, June, and so on. If we have a situation where the curve is flat, this means that the volatility is expected to remain stable. If we have a curve that's in backwardation, so remember, backwardation means that the curve is downward sloping. Here, the volatility is expected to be high in the short run, but this volatility is expected to come down. And the third possible situation is contango, where we have relatively low volatility for short-term futures contracts, and as the maturity increases, the volatility is expected to increase. The next point is that VIX futures may not reflect the index, especially when VIX spikes. So here again, we need to draw the distinction between the VIX index itself, which is what we talked about over here, and VIX futures, which are based on the index. There might be a situation where there is a sudden concern in the market and the VIX index spikes, but this is a short-term spike which will not have a huge impact on VIX futures that will expire in a few months' time. So therefore, VIX futures do not necessarily reflect the current value of the index. However, VIX futures converge to the spot VIX as expiration approaches. So the two, in other words, the VIX futures and the VIX index must be equal at expiration. The final point has to do with VIX options. These VIX option prices are determined from VIX futures. they provide an asymmetric exposure to potential increases or decreases in anticipated volatility. Now here I've reproduced an exhibit from an earlier reading where we had a mini case related to options on VIX index. The situation there was that our investor expected the market to crash, and therefore he was expecting that the volatility will spike. To take advantage of this spike in volatility, or the expected spike in volatility, the investor was going to buy call options on the VIX index. So it would make sense to spend a little bit of money on these call options, and if the volatility did indeed spike, then these call options would expire in the money. The option strike in this context is not a stock price, it is actually the VIX index. And also note that here the stock market might be crashing, so the stock market would be going down, but these call options, which are based on the VIX index, would be increasing in value. Moving on to variance swaps. A variance swap allows directional bets on implied versus realized volatility. The payoff for a variance swap is given by this formula. At expiration, the settlement amount is equal to the variance notional multiplied by the difference between the realized variance and the variance strike. The variance strike is established at the start of the swap, and this variance strike is based on the implied volatility. So this is the implied volatility when we get into the contract. If the realized volatility over the life of this swap is high compared to the variance strike or the implied volatility, then the payoff will be positive. On the other hand, if the realized variance is low compared to the variance strike, then the payoff will be negative. So you need to learn this basic formula, which is the variance notional times the difference between realized variance and variance strike. Variance swap traders generally agree on these two items. The first is the variance swap trade size expressed in Vega notional. Vega notional gives a sense for the profit associated with the swap if there is a 1% change in volatility. So if the Vega notional, which is also written as N Vega, is 50,000, this means that if the realized variance is 1% more than the variance strike, then the profit will be 50,000. The other variable that is defined up front is the strike. This represents the expected future variance of the underlying, and it is expressed as a volatility. To convert this volatility to variance, we simply need to square it. Now, given 1 and 2, the variance notional is calculated using this formula. So this is the Vega notional, which can also be written as N Vega, divided by 2 multiplied by the strike price. The settlement amount then can be written like this. So this settlement amount is the same as what we have up here. Instead of variance notional, we now use this formula. So we have N Vega, and then we have 2 times the strike price. So this thing in red is essentially the variance notional, where we have used this formula. And then this expression over here, sigma squared minus x squared, this is the realized variance minus the variance strike. So this is the realized variance, and this is the variance strike. The next formula is the variance swap at time t. So let's say that the swap starts at time 0. We are currently at point small t, and the swap expires here at time big T. So the value at time t is given by the variance notional, which we've calculated over here, times the present value factor. So it is the variance notional, and then we calculate the present value over here, so we will have to discount back. Then we have small t over big T, so that's this distance over here, which is small t, divided by big T. So it is the fraction of time that has gone by so far. Then we have the realized volatility. So the realized volatility between here and here, plus big T minus small t over t. So that then is this fraction. So the fraction of time from here to here relative to overall time. And then we multiply by implied volatility over the remaining period and then subtract the variance strike. We will apply this formula in an example on the next slide. A feature of variance swaps that makes them particularly interesting to investors is that their payoffs are convex in volatility, and that is shown over here. So notice, as volatility increases, the variance swap payoff shown on the y-axis increases more than this linear function. And you notice that as the volatility keeps going up, this payoff increases more and more relative to simply a linear increase. And this is very useful for investors, and therefore the sellers of these contracts can actually charge a premium because of this convexity. Alright, so now let's go over an example which deals with variance swap valuation and settlement. Olivia Santos trades strategies that systematically sell volatility on the S&P 500 index. She sells $50,000 Vega notional of 1-year variance swap on the S&P 500 at a strike of 20%. This is quoted as annual volatility. So the 20% is a volatility. For variance, we'll have to square this. Now, 6 months have passed and the S&P 500 has experienced a realized volatility of 16%. On the same day, the fair strike of a new 6-month variance swap on the S&P 500 is 19%. So let's just understand what's going on here. So this is a 12-month swap. We are now at the end of 6 months. So this is actually small t and big T is over here. You need to determine the current value of the swap variance sold by Santos. So at this point, small t, you need to determine the value. So I've also reproduced the solution and I'll just walk you through this solution. Here is the formula that we discussed on the previous slide, and we need to identify all the relevant data based on what is given here. First, we need to come up with the variance notional, and as we discussed, variance notional is Vega notional divided by 2 into strike. Vega notional is 50,000 and then 2 times the strike is 2 into 20. So this gives us our variance notional. Then we need to apply the present value factor, and that is shown over here. The present value factor simply uses the interest rate of 2.5%. Then we have small t over big T, which is simply 1 over 2. It's actually 6 over 12, but that becomes 1 over 2. And then we have the realized volatility over the first 6 months. We are told that the realized volatility is 16%. That's shown here. And then we need to square it because we want the variance, and that gives us 256. So this is where all the numbers are shown. 1250 is coming from here. This is the present value factor. And then we have 6 over 12 times the realized volatility plus 6 over 12, because this fraction again is 6 over 12. So 6 over 12, which is 1 over 2, times 361. So 361 has to do with the implied volatility. We are told that the implied volatility over the remaining 6 months is 19. The square of 19 is 361. So that's over here. And then we need to subtract the variance strike, and that is 20 squared, which is 400. So that's coming from here. So the strike of 20% quoted as annual volatility, we need to convert this to a variance, and to convert to variance we make it 20 squared. So this formula is not as complicated as it looks. We plug in the numbers and get this number. Given that CentOS is short the variance swap, the mark-to-market value is positive for her. So the point here is that this formula is for the long party. So if we get an answer that's positive, then that would be good for the long party and bad for the short party. But here we have a negative value. So negative for the long party would mean positive for the short party. So the short party has a benefit of this much. Then next we need to determine the settlement amount at expiration. And this is much simpler, and I believe that on the exam you are more likely to get a question related to the final settlement amount or the payoff at settlement. So we need the variance notional, which we calculated up here. So that's 1250. And then we have the realized variance, which is 18 squared, and that is given over here. So realized variance minus variance strike, which is 20 squared. So this is minus 95,000. And again, this is from the perspective of the long party, but Olivia Santos is short. So from the short party perspective, the benefit is going to be plus 95,000. So that is how much Santos will receive.